Well, hello everyone. Thanks for allowing me to participate in the EOF. First of all, introduce myself. My name is Jhon Mojica. I am research associated at the Center for Global Sea Level Change, a group from the New York University Abu Dhabi. And today I'm going to talk about the submesoscale mixing features in the Gerlache Strait base. Just to inform you, this is part of a publication already submitted in the Science Marine Bulletin just a couple of months ago. Well, first of all, let me start with the study area. In this case, it's the Antarctic Peninsula. And well, here I'm going to show you the Antarctic ice velocity map from RIGNA 2011, where we identify the relevant areas with higher ice melt rates. And well, as you can see, the Antarctic Peninsula is one of them, where it's located at the west side, the Gerlache Strait, that is basically 150 kilometers long and 10 kilometers wide, with an average depth of 600 meters. Within, we can identify three main interior bays from south to north, Flanders, Antwerp, and Charlotte. In general, the circulation here is from south to north, with some inputs of different water masses, such as the upper circumpolar water from the south, the transitional when it comes in water from the between Ambers and Brabant, and also some part of the Weddell Sea waters that come from the north. But in this strait, as a problem statement, we can identify a lack of information or data that doesn't allow us to characterize the impact of the input of different water masses that can impact directly the marine terminating glaciers that are mainly located in the three main bays that I previously mentioned. And well, that's why our aim for this work is to characterize the ocean dynamics in the Antarctic West Coast at multiple scales, particularly qualifying and quantifying the mixing and dissipation processes and their temporal and spatial variabilities. But as a group, we got the opportunity to participate in the Antarctic Columbian expedition from December 2018 until January 2019, where we planned a high-resolution survey based on the equipment we got. In this case, to record ocean fine structures, we used a CTD, a conventional CTD to work. And to record the microstructure, we use a VMP, that's a vertical measure profiler, with a distribution from the mainstream of the Gerlache Strait to the main interior bays that were allocated the marine glaciers. Here, just I want to present you the main equipment, basically this tube with the brush on the top, but basically consists of a couple of sensors, such as two shear proofs, one microtemperature sensor, one microconductivity sensor, one pressure one, and one tilt sensor. This one helps us identify if the equipment is falling, present a free falling and doesn't present tilting, that allow us to quantify the vertical shearing during the deployment. Also, in addition, we got, as already mentioned, the seabird, and in total, from the area and the survey, we got 14 CTD stations and 26 of 30 stations initially planned. And that's because of the interior of the Charlotte Bay, we identify, we got a high amount of ice that doesn't allow us to go inside the bay. Well, here just I want to show you some part of the deployment. Something important is that the sensors on the bottom are so delicate, so we have to take care of those during deployment. We have to put on the water, the device. And something important here is that we have to give him some slack of a rope in order for the free fall. And the idea, is just to avoid these loops or up and down movement that can impact the calculation of the vertical shearing. And the rope, to know how deep we can reach, is because we have a measure, the rope is measured every 15 meters, so in that order we can identify how deep we can reach. Here, just in general, of general equation and theories that we are following for these calculations. And well, we use motocross and AirSync to process the data in this recorded by the MP. Also, as I already mentioned, we just use the freefall data. Yes, as you can see, it's a clear pattern to reach the depth we want to reach, and well, to back, we have to use for manual force. That's why we have some bumps here, and those ones are discarded, the upcast. So that's why we just consider the downcast. And well, for processing and so on, filtering the data, we use some script from MATLAB. Well, in general, as I already mentioned, here we have the tree base. We have taken count A is in the south, Flanders, B Ann-Bor in the middle, and C Charlotte. Those three in such a small space or small area can identify different areas and trendings that are conserved during the full study period, and of course can affected and impacted by the different water masses. So we can identify here the most relevant one at the north. We have a warmer waters, of course, shallow but still warmer than the one that we identify here in Flanders that can impact, of course, these areas in the glacier part. But also something relevant here for the Flanders thing is that the deeper waters, yes, also are warmer, but even in almost 2 degrees if compared with the ones recorded in Charlotte. We can identify by the buoyancy or lower level of stability in the area, and that's why the system in general is prone to be affected by some inputs of different waters. Well, here at the top left, there is a general dissipation rate profile for each bay. It's clearly variable among those. And we can identify a higher mixing at the subsurface, at the glacier, yes, with a higher variability, and some specific depths in the other ones, the other bays, that help us to identify and characterize that this is maybe produced by some subglacial melting and located in some specific areas. Here at the bottom left, there is a comparison of the dissipation rates just between the mainstream and the basin tissues. And as we expect, there is a higher values of the mainstream, of course, because of the dynamics in the area. And well, at the right side, you can see the dissipation rate at 50 and 200 meters depth, showing that there is a higher dissipation rate at the northern station, yes, if we compare again with another stations, and again higher at the subsurface waters. Well, all this data help us to create for the first time in the area a diagonal diffusivity map of the tree base. As we can see, there is a small variability in station that help us identify some transitional and smooth variation. Also, we can compare with the variability at the different depths and bays that are more remarkable. We can calculate a variability that can reach, in some cases, from 1 to even 2 orders of magnitude between different stations and different bays. We can reach values around 0.5 until 3.5 if we compare Flanders with Charlotte. That indicates that in Charlotte, for example, we have a well mixing water in the north. Also, we can observe some hotspot, higher turbulence levels that may be associated with the interaction of the entrance of different water masses with resident waters and topography. In general, just to conclude, there is the first time a development possibility map that we create by the main base of the Everlach Strait. Also, there is a maximum variability that can reach almost between 1 and 2 orders of magnitude, as I mentioned, and help that we can identify special patterns that are related with the intrusion of different water masses, in this case, well, by the upper quality of water to affecting or impacting the resident waters that are matching with the location of the hotspots and of higher turbulence. As I already mentioned, this is part of the manuscript already. We already published just a couple of months. But thank you so much. And I don't know if you have any question. Welcome. Thank you.